Okay, so it's already time. Nobody has joined the live session. I'll wait for a couple of minutes and then I'll start solving the problems and you guys can watch it on YouTube if nobody joins. But yeah, if you're watching this, I really encourage you to join the live sessions. That way you can interact and ask your doubts if you have any. That will also allow me to better understand what problems you are facing. Okay, anyway, so I'll wait for a couple of minutes before starting. Okay, doesn't matter. Let's start with problem number one. Okay. 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 So the question asks us to find the energy of an electron confined in a cubic box. So note that the box is cubic, okay, which means we are talking about a three-dimensional system. And the size side of the cube is 2 angstroms. And we are talking about lowest energy state. So lowest energy state of a electron in a cubic box. Okay, and the options are okay. So these are our options. Here J is for joules. Okay, so let's draw a cube let's draw a cube like this. So this is the cube that we have, and we have an electron inside it. This is the electron. And now we are told that the electron is confined in a cube, which means if you draw the potential, everywhere outside the potential is infinite. Okay, so here you have infinite potential outside the cube, everywhere the potential is inside, and inside the potential is zero. Okay, so this is like extension of the one-dimensional problem which we solved in the last class. Here we are now extending it up to 3 dimensions. Okay, here we are now extending to it up to 3 dimensions. Okay, so when we have for a 1D case, right, for a 1D case, what is the energy? The energy is h square n square 8m a square, right, where a is the length of the box, okay, for 1D. Now when we extend it to higher dimensions, let's say for a 2-dimensional case, here instead of simply n, we will have nx and ny, right? We'll have these two. So the energy will be h square over 8m a square, and now nx squared plus ny squared. So the energy just adds up. Okay? Energy just adds up. Now similarly, for a 3D case, we will have E, nx, ny, nz, and this will be equals to nx squared plus ny squared plus nz squared. Okay, now for ground state, we take the minimum values, right? Ground state is the minimum energy state. Minimum energy state. Okay, let me bring it down. Yeah, fine. So here these nx, ny, nz, they go from not 0, they go from 1, 2, 3. So they are basically natural numbers, okay, positive integers starting from 1. Good. So for ground state, minimum energy state, okay, so the minimum energy state, we have nx, ny and nz, all of them will be equals to 1. Okay, all the integers will have the value 1, which is the minimum possible value, right? Therefore the ground state energy will be, okay, so this is the expression which we will be using because we are talking about a 3-dimensional case. Okay, so the ground state energy EGS, that will be nothing but h squared over 8 ma squared, and all of them are just 1. Okay, so this becomes 3h squared over 8ma squared. Okay, now we know h and we know m, we know a. So now all that is left is to just plug in the values. We know m for electron is 9.11 10 to the minus 31 kg, and a of the box is given to be 2 angstroms. Okay, so this is 2 into 10 to the power minus 10 meters. Okay, so just plugging in the values, we will get E ground state is equals to 3 by 8 into 6.626 into 10 to the power minus 34 whole squared over 9.11 10 to the power minus 31 times 2 into 10 to the power minus 10 again whole squared. Okay, so this will become 3 over 8 into 6.626 squared into 10 to the minus 68 over 9.11 into 4 into 10 to the power minus, this is minus 20 minus 51. Okay, so upon solving this, so you can see this is 10 to minus 17 and this is roughly 10 to minus 18. So this comes out to be 4.57 10 to the power minus 18 joules. Okay, so this is the answer. Let's see if it matches any of the options. Yeah, it does. It matches with option B. 4.57 10 to the minus 18 joules. Okay. Let us get to the next one. So problem number 2. Again we have an electron. And again it is confined, but this time it is confined in a one-dimensional box. Okay, and the length of the box is 1 angstroms. The question is, find the wavelength of the emitted photon for the transition of electron from second excited state to the first excited state. Okay, and these are the options. (65.2 angstroms, 20.22.3 angstroms, 86.8 angstroms, or 3.75 angstroms. Right. So let's look at the question. We have an electron which is confined in a one-dimensional box. So let's draw a 1D box. Yeah, it looks something like this. Correct. So outside the potential is infinite and inside the potential is 0. And this length is given to be 1 angstroms. Okay, this length is 1 angstroms, and we are required to find the wavelength of emitted photon. So find the wavelength of the emitted photon, and we have transition from second excited state to first excited state. Okay, so if the, let's say this is your ground state, then we will have first excited state, and then we will have second excited state. So the transition is here. So electron from here jumps here, and this emits a photon, and we are asked about the wavelength of this transition. Okay, fair enough. So let's start solving this. Okay, so we know that for a one-dimensional box, okay, if particle is in nth state, then the energy is given by, okay, so we just had a look in the previous question. What is the energy? Energy En is n squared h squared over 8m a squared. Okay, so first excited state means n is 3, n is 2. Second excited state means n is 3. Okay, and because the transition is happening from 3 to 2, so the energy difference is given by, let's say this is our final state, this is our initial state. Okay, So our delta E will then become h squared over 8ma squared ni squared minus nf squared. So this becomes 8ma squared. Now this is 3 squared, which is 9, and this is 2 squared, which is 4. Okay, so we can write this as 5h squared over 8ma squared. Okay, so this is the energy gap between the two states. Okay, delta E. Now once we know delta E, we can easily convert it to wavelength. How? Because we know that delta E is nothing but h nu, and nu is nothing but c by lambda. Okay, so this implies lambda is nothing but hc by E. So this is, let's say, equation 1, this is equation 2. Now putting the value of E from equation 1, so substituting equation 1 in equation 2, we get lambda is equals to, so this 1, okay, let me write down the complete thing, hc multiplied by 8ma squared divided by 5h squared. So this 1 square will cancel out with this h, so our lambda will be 8mca squared over 5h. Okay, now A is 1 angstrom, M is 9.1 into 10 to the minus 31 kg. Okay, and c is speed of light and h is Planck's constant. So plugging in the values, we get lambda equals to 8 into 9.1 into 10 to the minus 31, and then this is 3 into 10 to the 8, and this is just 10 to the, so squaring it will give you 10 to the minus 20, and divide the entire thing by 5 into 6.626 into 10 to the power minus 34. Okay, so this becomes 8 into 9.1 into 3 over 5.62, sorry, 5 multiplied by 6.626 into 10 to the power minus 9. Okay, so this is in meters. So finally, if we calculate, this comes out to be 6.5197 into 10 to the power minus 9 meter. Okay, so now because we have to convert it to angstroms, we can write this as 65.197 into 10 to the power minus 10 meters. Now 10 to the power minus 10 meters is angstroms, so we can write this as roughly 65.2 angstroms. Okay, so this is the final solution. Let's see if it matches with any of the options. Yes sir, it matches with option A. Okay, therefore we can see that when there is a transition from second excited state to first excited state for an electron in a one-dimensional box, it will emit a photon of wavelength which is close to 65 angstroms. Okay, I hope this is clear. So let me write down the next one. So here is problem 3. Okay, and the problem is that we have an operator this is the operator, which is the double differential operator, and this operates on an eigenfunction. Now we discussed in the last class about operators and eigenfunctions in detail and what is the eigenvalue and stuff like this. So you can watch the previous lecture, or you can even watch the class material, and you'll get a fairly nice idea about operators, eigenfunctions and eigenvalues. So the eigenfunction is given to us as psi of x a times sine 2x. And question asks us to find the eigenvalue. The options are A, B, C, D, A to A4, A4, A to A, 4A, or 4. Okay, so this is the question. Now we discussed in the last class that if you have any function, okay, any function f for any function f, if operator d acts on it and we get the eigen equation which is d operating on f gives you lambda times f. So this lambda is a scalar. This lambda is a scalar and this is known as eigenfunction. So basically whenever some operator is operating on a function, so we must get the same function back, just multiplied with a scalar. Okay, so in this example, our eigenfunction is given to be psi and it is a sine function. Okay, so basically when our operator d, which is a double differential operator, when it will operate on psi, we are expecting that we will again get back a sine function multiplied by some scalar, and the question asks us to find the value of that scalar. Okay, here let's start. Our operator is also given to us as minus d2 over dx squared. Okay, so let us operate. Okay, let us operate. So let us compute what is the value of this thing. Okay, so this we can write as dy dx and then dψ by dx. Okay, now dψ by dx will be, so this will be d by dx of a sine 2x, and now we will simply differentiate this. So a is a constant, it will come out. Differentiation of sine is cos, okay, and then we'll multiply it by 2 because of chain rule. Here we have 2x, right? So a factor of 2 will also come. Okay, so then this becomes 2a cosine 2x. Now again differentiating this, okay, again differentiating this, we get d2 psi over dx squared. It will be d by dx of 2a cos 2x. Okay, so 2a, and differentiation of cos is minus sign, so we'll get 1 minus outside, and again this will be multiplied by 2. So then this simply becomes minus 4a sine 2x. Okay, therefore we can say that minus d2 psi over dx squared is nothing but 4a sine 2x. Now if we look at this quantity, if we look at this quantity, okay, this is nothing but psi of x, right? This is nothing but psi of x. Therefore we can write our operator, which is minus d2 over dx squared. When it operates on psi, we get 4 times psi. Okay, therefore by the definition this is the eigenvalue. Okay, so the correct answer is 4. Okay, yeah, okay then. Let me now write down the next one. Okay, So we are given a normalized wave function for a 1D box of length L, and the rigid walls are located at x is equals to 0 and x is equals to L. Now the question is that what will be the nature of variation? The nature of variation of psi 3 squared. Now this is a way of writing probability density. Okay, and here n is 3, which means the second excited state in the range 0 to L, and we are given several options and we have to tell which one does it fits with. Okay, this is the wave function, and now let me draw 4 boxes. Okay, which say this is 0, this is L, and this distance is 2 by L. Let me draw one more line at L by 2. Okay. One more at L by 4, and finally one more at 3L by 4. Okay, now let me copy this thing. Okay, so good. Now this is option B, C, and B. And now let me draw the curves. So option A goes like this. Okay. Option B goes like this. Okay. Now C goes like this. And D goes like this. No. So it has this L by 2. Then again it has 2 divisions. Here and 2 more here. Yeah. Okay, so this is L by 6 L by 3 and 2L by 3 and 5L by 6. This is N by 2, 12 by 3 and 5L by 6. Okay. And the wave function, it looks like this. Okay. So basically we are given a wave function. This psi is the wave function which is given to us. Okay, and we want to find out the value of psi 3 squared, like how its functional form will vary between 0 and L. Okay, now let's write the function again. So here we have psi n x, it is given to us to be under root 2 L sine n pi x over L. Okay, now for n is equals to 3, we get psi 3x to be equal to under root 2 over L sine of 3 pi x by L. Therefore, okay, therefore mod psi 3x squared will be, so this will become 2 over L and sine will become sine squared 3 pi x over L. Okay, now in the four options we note that they have minima and maxima at different places. So let us just compute minima and maxima. Okay, let's say this is our function. Let's say we call this as some function f of x, and let's first find out what will be the first derivative of x. So this will be 2 over L and this is sine squared, so this will become 2 sine 3 pi x over L, and then cos 3 pi x over L, okay, into 3 pi over L. Okay, so this is basically 2 sine theta cos theta, and we can write this as, so this will become 6 pi over L squared sine 6 pi x over L. Okay, now we know that the minima and the maxima occurs when f prime x is 0. This gives us minima and maxima. Okay, so if f prime x is 0, this implies that 6 pi x over L, this is nothing but a multiple of pi, so this is basically n pi. Okay, so these pi's will cancel out, and we will get x to be n L over 6. Okay, so here n is basically 0, 1, 2 and so on, and plugging in these values of x, so we'll get x at 0, L over 6, 2 L over 6 which is L by 3, and then 3 L over 6 is basically L by 2, 4 L over 6 is 2 L by 3, and 5 L by 6 and L. And because we are concerned only in the region 0 to L, okay, so these are all the values of x where we will get either a maxima or a minima. Now if we look at our plots, here, we see that clearly option D matches with our values, because here we can see that it is minimum at 0, maximum at L over 6, again minimum at L over 3, and so on. Okay, which is not true for rest of the these rest of the problems. Okay. Now again we can also find out that if this value is L by 2, so we just have to put L by 6 in fx. Okay, here is fx, here is fx. Okay, let me shift this a little down. Yeah, this is fine. Okay, so at x is equals to, let's say, L over 6. Okay, at x is equals to L over 6, we will get mod psi 3 squared. This will be 2L sine squared 3 pi, and x is L over 6, so this LL will cancel out and will left with 6. So this will be pi by 2, which is 90, and sine of 90 is 1. So this entire thing gives you 1, which implies that mod psi 3 squared is simply 2 by L, and which matches with our plot. Okay, so this is therefore the correct answer. Okay, let's solve next one. This will be question number 5, I guess. Okay, find the value of normalization factor A in the azimuthal wave function in one electron atom given by y is exponential iota ml 5. Okay, where this ml is an integer, it can be positive or negative. Okay, so the options are 1 over pi, 1 over 2 pi, 1 over under root pi, or 1 over under root 2 pi. Now any wave function psi of x any wave function psi of x is normalized if integral mod psi x squared dx is 1. Okay, as the particle exists somewhere, because this is the probability density that this mod psi square is 1, so probability of finding the particle everywhere, that total should be 1, right? Because sum of probability is always 1. Okay, so this is the normalization condition. Okay, now here the difference is that we no longer have the Cartesian coordinates x, y, and z, but we have the polar coordinates, the spherical polar coordinates r, theta, phi, and we are given the azimuthal wave function. So here instead of dx we will have phi. So for this problem our integral will go from 0 to 2 pi. Instead of psi x we will have our phi of x. Okay, we will have our phi, instead of psi we have phi, and mod squared phi d phi, integral 0 to 2 pi, this should be 1. Okay, this is the condition, and here this term is nothing but phi star phi. Okay, phi star phi. So now let's solve this. So first of all, let's find out the value of phi star phi. So our phi star will become a times e minus iota ml phi multiplied by a times e to the plus iota ml phi. Okay, and this is nothing but a squared e to the minus iota ml phi and plus iota ml phi. So this is 0, so then this is nothing but a squared. Okay, and now if we put this in integral, we get integral from 0 to 2 pi a squared d phi is simply 1, and because a is a constant we can just pull this out of the integral. This will be a squared integral 0 to 2 pi d phi is 1. So this simply implies, so this integral will become 2 pi and a will become a will become 1 over under root 2 pi. Therefore, D is the correct option. And this phi we can now rewrite as, so our phi will become 1 over under root 2 pi e to the iota m l phi. So now this is our normalized azimuthal wave function. Okay, and this is what we also saw in the lectures when we were solving the Schrodinger's equation for hydrogen-like atom. Okay, now wait for a minute, I'll drink some water. Okay, so this was what, question number 5. Let's move on to question number 6. Okay, I've lost my internet, but it doesn't matter, does it? Because there is no one in the online class, and I will be uploading the recording on YouTube. Okay, so let me wait for it to come back. Okay, internet is there. Yeah. Hmm. Yeah, so we are back. Okay, so let me also now write down the last part, which is 1 over pi a naught cube squared root e to the minus r by a naught. Okay, so let us first try to understand the problem. It is very simple problem. We are given a wave function for hydrogen atom. Okay, wave function for hydrogen atom, and it is the ground state wave function psi 100. So this is basically our value of n, l, and m, which are the three quantum numbers associated with the wave function of a hydrogen atom. Now this is just the normalization factor. Okay, this is the normalization factor, and this is the functional part. So we can see that our function is exponentially decaying function, right? So as our r is increasing, psi is decreasing exponentially. Okay, so that is fine. Here it is given that a naught is the radius of the smallest Bohr orbit. So basically this is our Bohr's radius, and r is the distance of hydrogen nucleus from the electron. Okay, r is the distance of hydrogen nucleus from the electron. Now what we are asked is to find the probability density function, okay, for the electron related to the nucleus. So what we are interested in is finding the basically our probability density function, okay, this thing. So this is what we want to find out. Okay, So yeah, and let us begin. Okay. The wave function psi 100, this is given to us as 1 over pi a naught cube square root over the entire thing, and then we have exponential function here and minus r over a naught again. Okay, now the probability the probability density function of the electron relative to the nucleus is given by mod psi squared, which is nothing but psi star psi. Okay, this is the same thing which we did in the previous question, right? So now here note that psi star basically, so our wave function psi is a real wave function. It is not a complex wave function, so its conjugate psi star will be the same as psi. Okay, so both of them will be same. Anyway, let's write them out. So this will become under root 1 over pi a naught cube e to the minus r by a naught, multiply this thing by 1 over pi a naught cube into the minus r by a naught. So this will become simply, okay, this thing. Let me rewrite. Okay, and then this will just becomes, okay, so this is our answer. Okay, this is our answer. Let's see if it matches with any of the options. It matches with option A. Okay, good. Now let's do a follow-up question. Let's do a follow-up question, which will be, I think, question number 7. If I'm not wrong. Using the wave function given in previous question, or the ground state of hydrogen atom, find the most probable distance r of the electron from the nucleus. Okay. Okay. So we were given a wave function in the previous problem. Let us rewrite the wave function here. So this is the ground state wave function, and this was given to be under root 1 over pi a naught cube e to the minus r by a naught. This was the wave function given to us. Okay, so this is the basically ground state. This is the ground state, and we are asked to find the most probable distance r of the electron from the nucleus. Basically, what will be the most probable distance? So yeah, let us start solving this one. So the probability that the electron is found between r and r plus dr from nucleus is given as prdr psi star psi 4 pi r squared dr. Okay, so where this 4 pi r squared dr, this is the elementary volume between the shells of radii r and r plus dr. Okay, so then we can write our prdr. So we have already computed the value of psi star psi in the previous question. Okay, we already have this value, so this is nothing but 1 over pi a naught cube e to the minus 2r by a naught, and then we multiply this thing by 4 pi r squared dr. Okay, so this basically then gives us pr. This pi will cancel out, so pr is nothing but 4 over a naught cube r squared e to the minus 2r by a naught. So this is PR. Okay. So when we are asked to find the most probable distance where our electron is, and this is the probability of finding the electron at any distance r. So the most probable distance will be the one where the probability is maximum. Okay. So most probable distance, let's call it r naught. So at this point our PR is maximum. Okay, so if PR is maximum, then we know that d by dr of PR at r is equals to r naught, this will be 0. Okay, which means 4 over a naught cube, and this will become 2r exponential minus 2r by a naught plus r squared exponential minus 2r by a naught into minus 2 by a naught. So this is 0, and this basically implies if we take this factor of 2r outside, it will become 8r over a naught cube, and inside we will have, okay, we can also take the exponential function outside like this, and inside we will have 1 minus r over a naught is equals to 0. So this is 0. Okay. So now this gives us three possibilities. Either r is 0, or e to the minus 2r by a naught is 0, or 1 minus r by a naught is 0. So this is r is equal to 0, this means nucleus. Okay, this means nucleus, so this is not possible, and this means that r is infinite, which is again not possible because we are talking about the ground state of the hydrogen atom. So from this we get r is equals to a naught, okay, which is the Bohr radius. And if you think about it, this is also the most logical solution, because the definition of Bohr radius is actually for the ground state of hydrogen atom. From the Bohr's theory, if you remember, a naught is the distance of the electron for the first orbit, which is the ground state. Okay? Therefore, from quantum mechanics also, we are getting the same thing, that the electron is most probably at a distance a naught from the nucleus when it is in the ground state. Okay, so let's pick the correct answer, which will be option D. Let us now solve the next one. So this will be question 8, correct? This will be question number 8. Okay, now again we have hydrogen atom, and again we have ground state, and the ground state wave function psi now is similar to the earlier problems, but now it has an additional sign factor, which is sine omega t. Okay, let us write the question now. So we will now consider two hypothetical shells which are centered at the nucleus, just like in the previous problem. In previous problem also we considered two shells separated by distance dr, right? This is also the same thing, and again they will have same radii r and r plus dr. Okay, the question is to find the average probability p of r that the electron will lie between the shells. Okay, and here are our options. So let us write our wave function. So wave function psi that is given to us is nothing but under root 1 over pi a naught cube exponential minus r by a naught, and then this thing multiplied by sine omega t. Correct? This is the one given to us. Okay. Now again, let us write the volume element. The volume element between the shells of radii r and dr, not dr but r plus dr, r plus dr. This is given as dv 4 pi r squared dr. Correct? Okay. So now probability p of r of the electron to be found between these shells is given as p of r dr, and this is mod psi squared dv. Okay, so let's now put in all the values. So this just becomes this thing, and this becomes 2 times r over a naught, and it becomes sine squared omega t, and dv we have already found out to be 4 pi r squared dr. Okay, so this pi will cancel out, so we will be left with 4 r squared over a naught cube e to the minus 2r over a naught, and we can write sine squared omega t as 1 minus cos 2 omega t divided by 2, and of course we have one dr outside. Yes, we have one dr. Therefore we can write pr, so this 2 will cancel out with 4, it will give us 2, so then this becomes 2 r squared by a naught cube e to the minus 2r by a naught, and 1 minus cos 2 omega t. So this is the probability of finding an electron at a distance r from the nucleus at any given time t. So if we revisit the problem asks us to find the average probability p of r, the average probability. Now if you look at this thing, and if we compute the average, let's say p of r average, if we compute the average of this thing, then we basically get 2r squared by a naught cube e to the minus 2r by a naught, and then 1 minus. So basically the average of cos 2 omega t over one entire cycle. Okay. Now we know that average of the cosine function, because it oscillates between +1 and -1. So the average of this function, it is 0. Okay, so this average is 0. Therefore, we can write P of r to be 2r squared over a naught cube e to the minus 2r over a naught. Okay, so this is our answer. Let's see if it is matching. Yeah, it is matching with option C. Okay. So if you want to see how this average is coming out to be 0, if you want to see how the average of cos theta is 0, then basically what one can do is we can write average of cos theta. So this is nothing but from 0 to 2 pi cos theta d theta divided by integral 0 to 2 pi d theta. This is how we find the average, and by doing this simple exercise we will see that average of cos theta is 0. So a cosine function over the entire cycle averages out to be 0. Okay. And that is why we converted this sine squared term in simple cos function. Okay, because average of sine squared will not give us 0. Okay, it will give us something. So yeah, that basically gives 1 by 2. So if you know that, then well and good. Okay, no problem. Now after this we can move to the next problem, which will be question number 9. Question 9. Okay. Just 1 second. So again, this is a one-dimensional problem. And wave function is given to be like this for x is equals to 0 to x is equals to 1, and psi x is 0 elsewhere. Okay? It is 0 elsewhere. And the question asks us to find the expectation or the average value x for the position of the particle. Okay, and it is given to us that a is a constant, and the options are the average value is a squared by 3, or under root a. Okay, so how do we go about solving such a problem? So we should know that for any given quantity s, the expectation value, that is defined as s times mod psi squared dx from minus infinity to plus infinity. Okay, this is how we define the expectation value. In this problem we are asked about x, and note that the psi is 0 elsewhere, so we can take limit from 0 to 1. Instead of s we can put x, and this will be mod psi squared and dx. Okay, now psi is given to be a under root x, which means mod psi squared will become a squared x. Therefore, the expectation value of x will become from 0 to 1 a squared x squared dx, and taking a squared outside, we can write this as a squared 0 to 1 x squared dx. Now integration of x square is x cubed by 3, like this, and we will put limits from 0 to 1. So this will become a squared by 3, 1 minus 0, and therefore we have x as a square by 3. Okay, which matches with option C. So this was a pretty straightforward problem. Once we know how to define the expectation value, okay, the expectation value, which is the average of any quantity s. So this is how you define the expectation value. Once we know the expectation value, we know how to get to the answer. Okay, good. Let's solve problem 10. Okay, so basically question 10. Maybe this is the last problem for today, or maybe we'll solve one more. Let's see. Question 12 question 10. Okay, so let us write our standard notation, which is 2s plus 1, and here we have j. And if we compare it with 2p 3 by 2, we get that s is half, we get that sp, which means l is 1, and we get that j is 3 by 2. Okay, just on comparison. Now we know that when we apply magnetic field, okay, so on applying magnetic field, the number of states in which the ground state splits is 2j plus 1. Now here j is 3 by 2, which implies 2j plus 1 is 2 into 3 by 2 plus 1, which 2 cancels, which becomes 4. So correct option is 4. Okay, so this will split into 4 states like this. Okay, so on applying magnetic field, we'll get 4 states. So yeah, I think we have some time left. Let's do one final problem. Okay, give me a minute. Okay, so last problem for today. This is problem number 11. The wave function of a particle is given by psi is equals to 1 over under root phi naught plus iota phi 1, where phi naught and phi 1 are the normalized eigenfunctions. So these are the normalized eigenfunctions with energies E0 and E1 corresponding to ground state, and first excited state. Okay, so E0 is the energy of ground state, E1 is the energy of first excited state, phi naught is the normalized eigenfunction for the ground state, and phi 1 is the normalized eigenfunction for the first excited state. Now the question is the expectation value, of the Hamiltonian in the state psi is, and our options are E naught by 2 plus E1, E naught by 2 minus E1, okay, E naught minus 2 E1 by 3, or finally E naught plus 2 E1 by 3. Okay. Now as defined earlier, so let's first rewrite psi. Okay. So psi is 1 over under root phi naught plus iota phi 1. Okay. As defined earlier, the expectation value here we are asked for Hamiltonian, that is given as psi h psi over psi psi. Okay, so this is normalization of psi, this is normalization, and this is average. Okay, this is average, and this is what we defined in the previous problem. So this is nothing but like h psi star, or let me write mod psi square dx minus infinity to infinity, and if this is normalized then this is just 1. Okay, yes, okay. Okay, so anyway, so let us rewrite this again here. Psi h psi over psi psi. Okay, so let's first compute h of psi. Okay, what is this thing, h of psi? So this will be nothing but h of 1 by root 2 phi naught plus iota phi 1, like this. Yeah, right. Now if we operate the Hamiltonian, so we know that h of phi naught is E naught and h of phi 1 is E1. Okay, so then basically these things become, so psi h psi, then this thing simply becomes 1 by root 2, and here we will have phi naught, and this will become minus iota phi 1. Okay, and this will be E naught by, sorry, this is wrong, this is like this, phi naught plus iota phi 1. Okay, so this is 1 by root 2, 1 by root 2 becomes E naught by 2, E naught by 2, and this becomes iota, iota is minus 1, and there is 1 minus here, so this just becomes E1. Okay, something like this, yeah. So this becomes E naught plus 2 E1 by 2. Now let us also normalize this thing. So let us compute this thing. So here you can clearly see that this thing will become, so instead of E naught and E1, so we will simply get 1 by 2 plus 1. Okay, just following the same method. So this will become 3 by 2. And then when we divide it, so using both these things, basically dividing, so we'll get h as, so this 2 and 2 will cancel, so this will become e naught plus 2 e1 by 3. So option D. Okay. Yeah. So yeah, that is time, and hopefully you guys will join in the next session so that we can have live interaction. Please watch the lectures before joining the tutorials, because I, for the most part, assume that you have watched the lectures and now you are here to discuss some problems, how to approach some problems which are also there in your assignments. And if you are not there in the live session, then I am not really sure if these sessions are helpful or not. uh, Also, if you have any doubts, you can ask in the forums or the comment sections of the YouTube, or you can even mail me at my email ID, okay, which is my name Manav Beniwal at iisc.ac.in. Okay, so yeah, that's it for today. Thank you for watching. I'll now end the stream.